Yeah, I think this group know Carolyn very well. I don't think I need to introduce her, but officially, hey, how are you? So Carolyn is official title is Associate Professor at Duke University, Division Chief of Cardiovascular Pathology, Director of Autopsy Service, my God, and Associate Residency Program Director. So a lot of responsibilities. And she graduated from University of Texas and residency training and fellowship training at Brigham and Women, very well known and fellowship trained, MD, PhD. So her interest, recent interest, I think, in addition to cardiovascular pathology, is the digital pathology. That's a very interesting topic, and that's a topic today she will share with us.
Great. Thank you for the introduction, and thank you for all on the call. This has been a very interesting topic. I've given several talks on it at different venues over the last probably 2 or 3 years, and I'm really excited to have the ear of expert cardiovascular pathologists, because I believe machine learning it's infiltrated a lot of the malignancy cancer diagnostics and kind of trickling into cardiology, not necessarily pathology, but imaging from the imaging standpoint, EHR data, and kind of also on the transplant space. So, I would love to hear your opinion on it. So I decided to pick this area of machine learning, digital pathology, and how it can be translated into a diagnostic. So I'm going to first share my screen here.
We're seeing the present.
Next slide thing here.
Yeah, if you can display settings and flip your to settings, it should be fine. The very top. Correct.
Here we go.
Perfect. Thank you.
Great, thank you. Okay, so the article I'm going to discuss today is entitled Deep Learning Enabled Assessment of Cardiac Allograft Rejection from Endomyocardial Biopsies. And this, the senior author of this paper was Dr. Faisal Mahmood, whom I do, we have started collaborating and kind of brainstorming ideas on possible future projects that stay not only on transplant, but cardiac in general. I'm trying to think of others that are involved here. Dr. Mitchell, I believe, was possibly involved in some of the annotation, but Jenna, she was a postdoc in Dr. Mahmood's lab while writing this paper. So the objective of this paper was, and I'll just quote it directly, present CRANE, which is the acronym for Cardiac Rejection Assessment Neural Estimator, a weekly supervised deep learning model for automated screening of EMBs in H&E stained whole slide images. So this is really good because when we diagnose things, we don't want to be looking at snippets of little things, as pathologists, we need to look at all of the tissue. So the model is based on whole slide images. Using multitask learning, the model can simultaneously diagnose ACR, AMR, QULT-B lesions, and concurrent mixed lesions, while an additional network was used to determine the separate rejection area. Okay, so background, I don't think I need to really go too deeply into background with this group, but as we all know, surveillance endomyocardial biopsies still remain the gold standard. And so pathologic diagnosis and agreement upon that is critical. And subtyping of rejection such as ACR, AMR, or misrejection, and the accuracy of that is critical to determine if we're going to treat, clinicians are going to treat. Most institutions are going to treat at ACR 2 or higher. And for AMR, my understanding, again, it depends, but it's usually going to be PMR2 that's going to be treated with. The severity of rejection is characterized by grade, as I said, and then this is a really interesting area, the identification of QULT-B lesions. In my training, I didn't see as many QULT-B lesions as I'm doing, as I see now, and some of those are very, very difficult. They can be mimickers, and you want to call infiltrating QULT, and I know there's probably a lot of intra-observer variability that goes to this. I think that was evidence even in our last SCVP teaching session where one person called infiltrating QULT, one person called grade. So that could be a very tricky area. So the premise for this machine learning, why do we need a tool? Why do we need machine learning to help us? And a lot of these papers or algorithms are going to be based on the logical fact that there's too much inter-observer variability when it comes to certain diagnoses. So this Nature Medicine paper referenced the Journal of Heart Lung Transplant consensus paper in 2011, which mainly showed the combined kappa value of all grades diagnosed between the 18 pathologists in this paper was 0.31, which is not so great. When they looked at 1990 grading system, and then it was on 0.39 when they switched over to 2005 grade. So kappa values are not, I'm not going to go too deeply into percentages or statistics, but kappa value is different from percentage. A 0.5 does not mean, half and half. In that sense, it'd be really bad, but it doesn't differ too much from, but it takes into account other factors. But still, so I will give you a reference for observed kappa value. So the kappa value ranges from -1 to 1. It's not the same as the percentage agreement. It takes into account the expected probability that groups would say either yes or no at random. Okay, so there's one of many published articles that say, okay, how do we translate that information? So less than 0 would be there's no agreement at all, and then you have slight agreement with up to 0.2, fair agreement at 0.4, 0.6, moderate, therefore. Okay, so a 0.39 is probably going to be at a fair, not so great. Okay, so machine learning algorithms may potentially improve the inter-observer variability. That's the main reason for why we developing such. This paper talks about in the background, previous attempts to algorithmically assess EMBs are limited because of the small data sets, and their population, if you look at the article, was over 6,000 slides, which is robust data. So yeah, that's all. So this is I'm just going to stop there, and if anybody has any comments on some of the papers that I referenced before I go into the method section. Anybody have any? Okay. So this is kind of the workflow, and I want to figure one of the workflow. We all know we have the biopsy, and then the US data set, all the data came from Brigham and Women's Hospital. And at Brigham, they have 3 slides with at least 3 fragments on each level. So acute cellular rejection, AMR, and then multiple lesions were the next output diagnoses, and then the grades were also. So they were trained, these slides were trained on data sets from Brigham, which is the US training set, and then there were thousands of slides from Turkey and many other slides from Switzerland. And then they used a weekly supervised, so algorithms can be supervised, weekly supervised, unsupervised. Usually that means if it's a supervised algorithm, at least from a pathologist point of view, that means that pathologists are defining what we say is truth by us annotating, rejection or not rejection. And it heavily relies on the input from the pathologist or consensus, hopefully, of pathologists. A weekly supervised algorithm, usually you annotate certain things, and then that can be, sometimes you can use computer modeling to be able to translate those few annotated things and you let the computer figure out. Unsupervised algorithms are going to be where you just tell them, okay, this is what, you show them the slide, this is what the outcome is, this is high grade rejection, this is not high grade rejection. We're going to have 0 input from anybody, including pathologists, that we're just going to have the computer figure out itself. Okay, that's probably the hardest thing to regulate, but there are unsupervised models that do that. For example, we don't know why the Tesla self-drives and ends up in the parking lot. They're unsupervised models. So the workflow, I will go into the model a little bit of those things. I'm not going to spend too much on the but okay, so Crane was developed on an internal data set about over using 1,690 patient biopsies from Brigham. Each biopsy had associated labels or diagnoses with rejection type, grade, and presence of the cold TB lesion. All cases diagnosed with AMR they were confirmed with C4D IHC staining. And this to me is, it's great that there was confirmation of C4D for AMR diagnosis, but is a little bit, one of my criticisms, I think, of the paper is, how we diagnose the I component of AMR differs across institutions, and that's well known. At Duke, we very, very high volume transplant center, and we do C4D IF most of the time. And so what we're introducing as what we call ground truth to train the algorithm, already there's a little bit of fault in the methodology there. Not to say that this is wrong, but I think that needs to be improved a little bit. The internal data set, okay, so we have all these slides from the US data set, and it went under training, validation, and a full depth test. That just means there was a separate data set of slides that were not involved in the training or validation that was used to separately test them out. Okay. So what happened, so the methodology of the actual algorithm, what we call transfer learning. I don't know how many computer scientists, math people are out there. Please chime in if there are. But anyways, when we use transfer learning, there's this thing called ResNet or ImageNet. Stanford has a program with actually ImageNet of actual pathology images and radiological images that they use. Millions and millions of images just for a computer to kind of learn basics. But usually for transfer learning, it's something called ResNet. And those images that a computer initially looks at to see what do feature extraction from are just letters or numbers or pictures of random things. When you show, you need some kind of library or reference to compare something. So anyways, transfer learning was used in this particular model. The extracted features were tuned based on what it was seeing, and I'll just show you I'll explain a little bit about transfer. So image classification is the task of taking an image and outputting a class. So, or probability of classes that best describes that image. So if, what we see as humans, our rods and cones see a picture, but what the computer sees is all these numbers. Okay, you're asking the program of the computer to perform complex math functions using a neural network. So every pixel has, this is a very, very generalized representation of what we do, our brains are doing, but every pixel is given like a red, green, or blue value when we're looking at the computer screen, iPhones, and you have a certain value that's, I guess, calculated based on an RGB value. Okay, the RGB color model it's a model in which red, green, or blue primary colors of light are added together in various ways. And it's used kind of for sensing, representation, and display of images across electronic systems, including our phones and digital scanners. So these primary colors maximize the differences between our cones and in our human retina, and then you see different wavelengths. So in our brain, we're kind of seeing a certain number. And then, we use linear algebra and fancy math equations to feed this into kind of what we call vector. We want a single layer vector information based on the number, and it goes through what we call a process of different layers. There's input layer, hidden layer, subsequent layers. And as it goes through, this data goes through these layers, it gets weighted. There's all these different, we call synaptic weights. And then it gets weighted, like, for example, if we have a picture of what looks like should be rejection, we told it this is what rejection is, but it's looking a little bit differently then, and if it gets it wrong, then it goes back to the whole cycle again. So kind of doing this weighted function. So in this paper, they took this US data set and then from Programma, they partitioned these slides into 70% of the slides were used for training, 10% of the slides were used for validation of that training set, and then the remaining 20% were used for independent testing. And the model performance examined across all different magnifications at 20, 40, 40, 20, and 10, which was resembling what we do. I'm sure most of us look at things in lower power, but there were some 10x model performance parameters. And this is the outcome data. So I think I have it. Oh, I don't have it different. Okay, so we can go through this one by one. Well, before I go on, does anybody have a question on what I just talked about, or have any comments on the methodology or anything? Editorializing. Okay, so the rejection here was overall rejection. So in terms of machine learning, we use a term called area under the curve, or ROC. That ranges, the closer to 1 it is, the better. Acceptable ROC or / AUC would be, I mean, a good algorithm usually now for cancer diagnosis is going to be above 0.95, 0.98. I think above 0.85, I think is reasonably good and definitely promising. And that's, again, based on what has already been done in the literature. So overall rejection here, in the US cohort, you can see this kind of blue line here. The AUC was 0.962. So overall rejection, the algorithm was able to detect correctly the truth that it was 0.96. That's a very good result. The 0.852 was on the slide. It was tested, and after it was trained, it was tested on the test set from Turkey, and it went down a little bit to 0.85. And then for the Switzerland group of slides, it was 0.84. And that's kind of expected for once you train on a certain training set of slides for the number to the AUC to go down, mainly because of a lot of factors such as, and you want to have introduced those common factors that differ against institutions and populations and scanners and all of these different variables, because this is real life. And so to have that independent test set from as many different institutions is important. It really strengthens what we call the generalizability of the algorithm. And that's the toughest thing, is to make sure that these things are generalizable and true, working across many different test sets that it hasn't seen yet. So for cellular antibody, for cellular rejection, ACR, the numbers were just very similar. That was just the overall that I just went over. For AMR, the training set results were 0.874, so it's about lower than the ACR. So a little bit lower performing, but still okay. And surprisingly, it didn't drop too much with an independent. Was able to recognize Colti lesion. And I don't know, one of my criticisms was, I don't know how many of these were infiltrating Colti lesions. It's not hard for me to diagnose a Colti A lesion. I don't really care about those. I care about those that are infiltrating Colti Bs that are very difficult from high-grade rejection. Because even if you, so you have infiltrating Colti lesions that you just don't have that edge of the endocardium, so you sometimes just don't know if it's high grade or not. Okay, so those are the results for that. We talked about the drop in performance in AUC when applied to external independent data sets. And this number is based on, it's kind of standard, and it's expected based on what's been done in the cancer world. If you in the algorithm, for example, the FDA approved one for Memorial Sloan Kettering for prostate cancer. That was tested. I don't know if it was tested at Yale, Peter, but I think that was one of the independent test institutions where it was tested. It dropped a little bit with the testing set, but it still did okay. It didn't drop below 0.8. Okay. Another part of the paper was that they wanted to see if they can help the clinician by producing these heat maps to help them focus on areas that you would otherwise not look at. Which I don't know if that's really a big clinical problem. It's one thing to write academic papers on something versus like what is really going to help me. So I'm kind of equivocal on that use case, but nonetheless, I thought it was creative to try to do these attention heat maps that are generated. And for example, they have this region of area, the computer learns that, and then it tries to map everything that looks like that area or that particular annotated area, and it maps all the areas that you should pay attention to. Let's say all the red. This would be great for something like cytology, where you're screening things and it takes you forever to figure out what you should pay attention to. In cardiac transplant, I'm not sure it'd be that much time saving, but I can see this being an application for another. Okay. I thought it was great that they investigated the limitations of the algorithm. They did a detailed analysis on the failure cases performed. All failure cases, the model has correctly assigned the height. So they make a point that, you know, for the algorithm that they made to bring the attention to, you know, areas that you should be concerned about, there were no incorrect triage type problems, but once you got to that area region of interest that you should be concerned about, they did have some mistakes. And these are I cut and pasted the ones that did not, where they made a mistake. So this is cellular rejection, based on the, and I guess this one, and it didn't really detail for me in the paper, like what it was called and what the computer called it. So it wasn't that helpful for me, but I don't know if that was called rejection when it was not, or I don't know what the problem was, but this was a wrongly called area. This test set, I don't know if that was a quality lesion and it should have been called something else. And this, I'm not sure. So they kind of make an effort to show you the photos of the quote unquote fail cases, but I couldn't really appreciate what the diagnosis was and how it failed. So that would be my thing. Okay, so the last part of the results I would like to go over was, and this is probably the most interesting to me, would be the comparison with human readers. So to compare the performance of the algorithm to that of expert pathologists, 5 certified pathologists from the mean experience of 10.5 years were recruited. The inter-observer variability among the experts and the variability between the algorithm and the individual experts was assessed. 100. So for this particular part of the study, 150 biopsies were randomly selected from the Turkish cohort. All the pathologists were blinded to what the diagnosis was, well, what the previous diagnosis that had been made. The cases were presented to the pathologist in random order through a digital web-based platform without any time constraint. And then the pathologists were asked to derive the diagnosis from H&E slides only without the use of IHC for AM. The average agreement for rejection between the individual pathologists, the kappa value is 0.537. So it was higher than the 2011 paper of 0.39. However, the 2011 paper was the 0.39 was between 18 pathologists, and this is only 5 pathologists, so that might be a factor. But anyways, average agreement between the individual pathologists and the algorithm was 0.63. So it seems to improve when you compare pathologists to the algorithm. It does better. There's more agreement. Okay. And this is a supplemental table that shows. So here we have, you know, P1 through 5 would be all the individual pathologists, and they're all looking at all these areas on the column. So if you compare pathologist 1 to pathologist 2, so part C is just human pathologists. So you have pathologist 1 compared to pathologist 2, and pathologist 1 compared to pathologist 3. So all the different combinations with 5 pathologists. So their agreement for pathologist and pathologist 2 for antibody-mediated rejection, the kappa value is really low. So apparently we don't do very well with histologic AMR, which probably is not a surprise to everybody here. Okay. So then for quilty lesion, again, and that's no surprise to me either, you know, the kappa value is, I mean, fair, a little bit below 0.4. The agreement between these 2 pathologists was the best on PCR. So these are the values. Seems like all the AMR is the concern for histologic AMR, because all the purple, you know, all the things to the left of the chart are all the light purple, right? And those are all AMR. And it seems like the agreement between the human pathologists do best on the ACR, mostly ACR and maybe quilty. Okay. But then if you are a pathologist and you're comparing yourself with the what the AI spits out or gives you, still, I mean, so it's shifted. The average kappa value is shifted. So there's better agreement there. So the purple antibody-mediated rejection, we still we did better, but a little better, but that seems to still be the most problematic. And then the ACR and quality kind of seem to be tied of doing the best and reaching even 0.8. So with this data, I think the conclusion was, definitely improves, whether it's a human or computer, improves in terms of variability. Okay, so my discussion points, that's all the data I'm going to present. So my discussion points for the group would be, would you use this algorithm? If so, would you prefer to use it as a synthesis tool or a primary tool? If no, would you want further validation of the algorithm or another test set before you actually adopted it? And what are the limitations at your own institution for implementing? Stop sharing.
Very good, very good. I think David have a question.
Yeah, so just a couple of informational questions. The call of antibody-mediated rejection, that was made without immunochemistry. How do people feel about the reliability of that? I must say I have difficulty, wanting to make that call without immunochemistry. I mean, I know people talked about things that seem to me to be very subjective, like endothelial swelling and whether or not there's, filling of some vessels with monocytes. I mean, I would be a little bit nervous about doing that, but I don't know. How do other people feel about that? That was one question I had.
You're not alone. I have a problem.
Okay.
Yeah, I would not feel comfortable just doing
Okay.
without HDM or IO. I mean, just the variability between healing injury and PMR, 1H is very high.
Okay. The second question I have is, well, there's another question. I remember an article, I don't remember the reference offhand, but this was an article done some years ago in which people were talking about, beware of areas that have previous biopsy artifact in it. And what they were doing, they had taken just some basically primates, I believe, and just did endomyocardial biopsies on these folks and then looked at them like maybe a week or two later. And what they saw were foci that they said at that time, again, this was a number of years ago, what could be interpreted if you didn't know the history as rejection. And so that's always made me a little bit nervous about, looking at areas. And as a result, I stay away from, I was told to stay away from areas of either previous scarring or previous fibrosis and things like that. Do you know if the computer program took that into account as well?
I don't think it was a directed, targeted, for example, healing injury or fibrosis. I don't think that was actually something that was in, apart from this study, we did a separate study that has not been published yet, but fibrosis, that's a great question for that reason, because healing injury and fibrosis is very common because you can have rejection in the setting of healing, right? Because
yes.
Right. So I didn't see that as a targeted, annotated area. So for the purposes of the study, I don't think it was.
But in terms of selecting the slide set that was shown to the computer system,
I'm sure there was, I mean, just by the math of it, I'm sure there were cases there where there were fibrosis and subacute healing injury, but I think that there should have been probably a, it was divided into ACR, AMR. I personally think there should have been a healing injury category, but I don't think there was. So
okay.
Yeah.
Okay, because I mean, I guess one of the things I wasn't unclear about, the images that were put to the computer system, were these pre-selected by humans in terms of trying to avoid areas like this, so that they basically just throw the whole biopsy at the computer?
Yeah, so from my reading of it, I think the only pre-selection variable was the fact that they knew what diagnosis it was, because you have to tell it if it's 1R, 2R, 3R,
Okay.
4. But I don't think, there's so many, there were like 6,000 slides. I don't think a person individually went through a slide. The diagnosis was already there, of course, but I don't think, I think the pre-selection was, the only pre-selection variable was the diagnosis.
Okay.
That had
I have
already.
a couple of other questions, but I want to give other people a chance.
Carolyn, can I ask you a question? I just didn't notice if they said this. Did they talk about situations where a difference between a 0 and a 1R is not that big a deal? Like that's okay. But if someone is calling something a 2R, that obviously changes management. So did they talk at all about how often they missed the 1R, 2R versus a 0R, 1R?
It might have been in the supplemental information, but I have to admit, I didn't have time to tease out every single supplemental information, but that didn't seem like an emphasis of the paper. Which I would, if I had to write the paper, I would do a algorithm that would be the binary point for me. 2R versus 1R, because that's the treatment point. And that's kind of what we did in our paper in progress, in a sense, and at the whole slide image level, right? Because you got to look at it. So I don't think that was a focus. I mean, this was a great paper. I mean, it was one of the first of its kind. But I think that's where, again, pathologists need to be involved, because these are the critical points and things that we need to look at, and will make a difference. That and infiltrating lesions, or
Max, if you mute yourself. Oh, well, Max is
there you go. There you go.
very good.
Is the algorithm generally available?
Yes, that's a good question. It's in my slide set, so I cut and pasted it. It's publicly available in GitHub. So there is a link where you can access it, and you can. I was just going to test it and validate it for my own curiosity in our institution. So it is publicly available. It's in,
Follow-up question, is this an online algorithm, or do you have to have special computer equipment
Yeah.
to be able to run this?
I don't know, I haven't done it myself. I'll let you know once I go through the process, but I don't think it requires too much IT infrastructure. Because it's a publicly available code, and then you can download it and probably, but I don't know if there's special software where you need, that's institution dependent. But once I do that exercise, I'd be happy to share my experience, see if I can help others.
I just looked at what they said about the code. It's in Python. So as long as you have Python and you have enough memory, you should be able to run this.
Yeah, but we can't underestimate the memory, because these slides, one slide is, yeah, it's a lot of data.
Right.
It's a lot of data. That's kind of the sticking point for a lot of, I think, institutions is it's easy to scan, but it's the most expensive to have to keep the data somewhere. And so,
So Carolyn, you comment on some C4D for antibody in your institution. I didn't catch that point clearly.
yes. So our protocol entails doing C4D immunofluorescence, not on every single one, but that is clinician driven. They have a clinical suspicions for AMR, and that can vary amongst clinicians as well. Then they give us an extra piece to do C4D immunofluorescence. We do have the option of, if we see a histologic suspicion for histologic AMR on H&E alone, we have the option, because there will be cases where we find it incidentally, right? And we don't have that extra piece. We have a C4D IHC that works fairly well, but we've also developed our own double stain here. And it's a PU.1 CD31 stain. That's beautiful because it's, well, just for visually, it's the PU.1 is a histiocyte marker, as you know, but it's very it's nuclear, and then you can see then, and then you have it, you have your nice CD31 stain. It's going to be, you know, the pink inside the nice brown, so it's very crisp. Versus, you know, you can get PU.1 staining or macrophage staining everywhere, right? With like Colty lesions or, you know, healing injury. And sometimes it's a challenge to figure out if that's really intercapillary. Oh, I think he's, Dr. Gordon, are you muted?
Yeah, I'm sorry. Just to add to that, at our institution, we actually routinely do C4D by immunoperoxidase on all of our biopsies, all of our transplant biopsies.
Yeah, it's a reflex routine.
Yeah, it seems to be, you know, easier to have it done right at the, I mean, make the diagnosis, you know, at that point rather than, you know, reordering and stuff like that. So that's, I don't know if that's justified, but that's what we do.
Yeah. Well, we have 145 transplants a year, so I don't think our lab can handle doing IF on every single case.
Yeah, yeah, I don't know how many we have, but we have a good number as well, so, but one, I guess, philosophical question that I have about AI in general, in this program in particular. Was there any discussion, or did the paper say whether or not the program, if it had a discrepancy, let's say a pathologist comes up with one cellular rejection grade and the program comes up with a different one, does the program have the ability to explain how it got to its diagnosis? Or does it just give you the answer?
So the due diligence was done where they actually published the quote unquote failed cases, meaning the diagnosis that was given by the pathologist was different from what the AI called it. I didn't, and from my cursory read on it, I couldn't tell why there was a disagreement or why it failed. The data might be there in the supplement, but it didn't really delve deeply into details of, the pathologist called this ACR, but then the algorithm called it, AMR or something else. The details were not there. The number of cases were not that high again, because like, at least on the US training set, the AUC was like 0.96. So, but they did show you the actual cases where it was discrepant, but it didn't go too much into detail. I'm sure it's there. I just haven't had time to look into it. And yeah, I wanted to know what they missed. And
I'm just a little bit nervous when you have a program that acts like a black box.
that's a perfect, and that's great for discussion, because that's the whole point about supervised versus unsupervised, and why I'm advocating for pathologists to be involved when, unsupervised algorithms, although it's fancy and great, and actually it's great for discovery, because you're like, wow, it saw things that we humans did not see, and it came up with this answer, but we just don't know why. So we don't know why, and then we can't regulate what we don't know.
Yeah,
So
I mean,
it's a little bit scary that way.
Yeah, I worry about things like, say a lab changes the chemical formula of the H&E stain or something like that, or some other thing happens, in terms of, I don't know, the chromophores or the coloring is different or something like that, that you don't know what goes into the program, then that can, I worry that kind of thing can happen.
Yeah, and that's why, and I think many people share the same thought, and that's why, and for example, College of American Pathologists has a whole committee, which I'm disclosing I'm part of, to figure out, okay, yes, an FDA algorithm is going to be approved, but how do we, okay, there was one independent tested at another institution. How do you know what it's going to do on your set of slides? You just don't know. And so, there are products and programs being built around how can we, do the QA part of these algorithms. I can send in my slides and how, based on my scanner and based on my, staining methods and protocol. So those are all things that I think people are taking into consideration as well.
Okay.
I was going to add that one of the things, Carolyn, you brought up was whether this would augment what we do or replace what we do.
Yeah.
And I think as pathologists, we'd all love to be augmented, not replaced.
They call it, anyway, sorry, augmented intelligence or whatever, but that sounds demeaning too, but anyways.
Yes, but it would be, if we think about what we do, we as pathologists need to evaluate cellular and antibody mediated rejection. We've just talked about how we really can't evaluate AMR on an H&E slide the same way we can do cellular. So it requires these two different modes. The only way I could see this replacing us is if it really could determine AMR based on the H&E slide that in some ways performs equal to or better than what we do on the complement staining that we all have to do to see this. And I should point out that all of the blood-based tests, whether you're talking about the old gene panel or even the cell-free DNA, cannot distinguish between antibody-mediated rejection and cellular rejection. And so to this day, I think we're still the only game in town to do that. And it'll be interesting whether someone can actually distinguish those two critical pieces because the treatments are so different among us. I'd be interested in other people's thoughts on that.
I would agree with you in terms of, it seems like we still have a job for a little bit, at least in terms of that. But I guess the other question that I would ask, and I don't know if the authors mentioned, I didn't see this in the paper, and that is, one thing that could supplant pathologists is that if by following the algorithms, they were somehow over time able to link this to better patient outcomes, you
Yeah.
know, then that would be something that I think we'd have to wake up and pay attention to. I mean, the crude analogy I would give is that, you know, cardiologists now no longer just rely on their stethoscope to analyze, you know, the degree of like aortic stenosis versus regurgitation. I mean, pretty much it's standard to use ultrasound, presumably because that's more accurate and presumably because that gives better outcomes in terms of planning for surgery and things like that. But I don't know if the authors even hinted that they were going to do some follow-up studies, for example, on these patients, say 5-year survivals, for example, or, you know, say a time to, you know, before the people have to maybe be retransplanted, or a number of, you know, severe rejection episodes, whether or not their predictions from this algorithm are better than, you know, the human eye. But I think that would be another thing that might, we would have to pay attention to, but sounds like they're not there yet.
Yeah. They're not there in the cardiac transplant world, but they certainly are in the cancer world where, you know, that's where all the I would say all the NIH money and also the industry money are focused on that patient outcome. You know, how can we find biomarkers that will predict response to a therapy? How do, you know, why are these patients responding better with this pattern versus these are not? And so that's where the focus is, patient outcome, where it should be. Yeah, definitely not there in this paper, but again, this is the first paper really introductory to, you know, to our field.
One thing, like in the paper, they compare inter-observer variability between pathologists as a very big thing, right? 0.3, 0.3. I wonder, has anybody compared this digital pathology using different algorithm? What their algorithm variability?
To MLs compared against each other.
Yeah,
Well,
that's
I'm gonna have to hurry up and make mine so we can have something to compare it with. Or others on the group here, feel free to build and we'll compare.
Peter, I completely agree with you on that.
yes.
Completely. Like how, if someone made a different algorithm on a different set of slides, how well do the two
What's the kappa value?
help each other? Yeah, what's the kappa value on that? And by the way, kappa values among pathologists are kind of historically, if you read lots of papers,
Yeah.
around 0.3 to 0.4. We are not good. It's hard to get a very high kappa statistic because of the way the methodology works. Like if you have one discrepancy, your numbers immediately start to drop down. And so I've seen a fair number of cap papers. I haven't looked at this in 15 years, but when I used to, it was a lot of stuff in the 0.3 to 0.4. So we are within the normal range for what people do for looking at dysplasia, comparing different levels like Barrett's esophagitis. It was not outrageous. We did not disappoint relative to our colleagues.
Yeah, yeah. Actually, and there were 15 of us where I went around and showed myocyte damage versus non-myocyte damage. Our consensus was like above 90%. And I just need to publish that. But anyhow, this was also a paper in 2011.
Yeah, I think for publication purpose. Yeah, I think for publication purpose, they purposely select one pathologist from Texas, from another pathologist from Turkey. So we compare it to that's. So, any more questions? If not, thank you so much, Carolyn. It's a lot of interesting discussion. Thank you.
Thank you.
Thank you, Carolyn. Very interesting.
Hi, everyone. Hope to see you all at USCAP in a week.
Okay, take care.
Yeah.
And
Are you be there, David?